Journey to Neptune, the farthest giant planet. Imagine having to plan a trip to the most remote place reachable by some incredibly long railroad. One of those spots so far out that even Google Maps throws up its hands and tells you, maybe you should reconsider. Well, Neptune is kind of like that. The last stop before cosmic nothingness. A blue giant that sits quietly at the edge of the solar system, completely indifferent to our attempts to reach it. The question everyone asks is simple. How long does it take to get there? The answer, as often happens when talking about space, is complicated. But let's start with the most surprising fact. In over 60 years of the space age, only one Earth-built spacecraft has ever visited Neptune. Just one. And it took a dozen years to get there. This lonely explorer was called Voyager 2, and its story deserves to be told from the beginning. It was the summer of 1977, and while the first Star Wars was hitting theaters on Earth, this car-sized probe was launching from Kennedy Space Center. Nobody on that August 20th could have imagined that what started as a 4-year mission to Jupiter and Saturn would transform into a 12-year and 5-day journey to Neptune, covering something like 4.3 billion miles or 7 billion kilometers through the grand tour of all 4 giant planets in the outer solar system. To put that in perspective, it's like going around Earth 175,000 times, or making a round trip to the Moon 9,000 times, numbers that make your head spin. But why exactly 12 years? Couldn't they do it faster? The short answer is no, not with available technology. The longer answer takes us into the fascinating and counterintuitive world of orbital mechanics, where nothing works the way you'd expect. Not enough for you? Well, if you really want to know more, you'll just have to keep watching the video. Let's start with the fundamentals. Neptune orbits at an average distance of 30 astronomical units from the Sun. 1 astronomical unit is the Earth-Sun distance, about 93 million miles or 150 million kilometers. Do the math. We're talking about 2.8 billion miles or 4.5 billion kilometers. If the solar system were a town square with the Sun at the center and Earth just 3 feet or 1 meter away, Neptune would be sitting 100 feet or 30 meters away, practically on the other side of the square. And it's not standing still. It moves along its orbit at 3.4 miles per second or 5.43 kilometers per second, which sounds fast but is actually pretty sluggish by planetary standards. So slow that it takes 164.8 years to complete one trip around the Sun. Since Neptune was discovered in 1846, it's only completed its full first orbit in 2011. Before then, no one had ever seen Neptune in the same celestial position twice. The fundamental problem is that you can't just point a rocket at Neptune and blast off. It would be like trying to hit a flying bird with a slingshot while you're spinning on a merry-go-round. Earth moves at almost 19 miles per second or 30 kilometers per second around the Sun, and this speed affects everything we launch into space. You can't get rid of it. It's part of the package. It's like we're on a speeding train and want to throw a ball at someone on another train traveling on a distant track at a different speed. Already complicated on Earth, let alone in space where you can't stop to take aim. Back in the 1920s, a German engineer named Walter Hohmann crunched numbers and figured out the most efficient way to travel between planets. His solution, elegant in its simplicity, involved elliptical orbits that touch the departure orbit at one point and the arrival orbit at the other. The problem? For Neptune, a Hohmann transfer would take more than 30 years. 30 years! Let's do the math to understand better. The transfer orbit between Earth and Neptune would have a semi-major axis of 15.5 astronomical units. Applying Kepler's laws, the same laws that govern the movement of all celestial bodies, we discover that this ellipse would have an orbital period of 61.3 years. But we only care about half the journey, so just 30.6 years. Basically, a probe launched when a baby is born would arrive at Neptune when that baby has kids of their own. As you can see, this isn't exactly practical. Apart from the fact that whoever designs the mission might be retired before the probe arrives, there's the small detail that electronics, batteries, and pretty much everything else would have serious trouble surviving that long in deep space. Cosmic rays, solar radiation, extreme cold, everything conspires against equipment longevity. And then, who would pay salaries and operational costs for 3 decades? This is where one of the most ingenious tricks ever invented for space travel comes into play: the gravitational slingshot. The concept is deliciously simple. Instead of going straight to your destination, you take a tourist route through the solar system, using the gravity of planets you encounter to give you a boost. It's like skateboarding and grabbing onto moving cars to go faster, except the cars are giant planets and the skateboard is a $500 million probe. But how does it work exactly? Imagine throwing a tennis ball in a moving train. If the ball hits the front of the train, it bounces back slower. But if it hits the back while the train is moving away, it bounces back much faster than it arrived. It stole some of the train's energy. Sure, the train slows down a tiny bit, but being enormously more massive than the ball, the difference is imperceptible. The same principle applies to spacecraft and planets. Voyager 2 was a master at this game. First stop, Jupiter, July 1979. The probe whizzed past the gas giant at 354,000 miles or 570,000 kilometers distance, stealing some of its orbital energy and shooting away faster than before. We're not talking about small increases. The encounter with Jupiter added about 6.2 miles per second or 10 kilometers per second to the probe's velocity. Hey guys, just a moment before we continue. Don't forget to subscribe to our channel, clicking on the notification bell, and leave us a thumbs up so you don't miss out on our daily videos. 2 years later, August 1981, it was Saturn's turn. Another boost, another course correction. The passage, just 62,760 miles or 101,000 kilometers from the ring planet, not only further accelerated Voyager 2, but aimed it towards Uranus with surgical precision. January 1986, Uranus. At each encounter, the trajectory was calculated with precision that would make a Swiss watchmaker pale. Getting it even slightly wrong would have meant completely missing Neptune. It was like playing billiards on a table the size of the solar system, where every shot had to be perfect. The beautiful thing is that this planetary dance can't be done whenever you want. The planets need to be aligned just right, and for the configuration Voyager 2 needed, you have to wait 175 years. 175. It's like the universe opens a window of opportunity and then says, "See you in a couple of centuries. Bye." It was a guy at the Jet Propulsion Laboratory, Gary Flandreau, who crunched the numbers in the 1960s and realized that between 1976 and 1980, there would be this miraculous alignment. He basically won the cosmic lottery. The outer planets would line up like pearls on a necklace, allowing a probe to visit them all in sequence. Without that coincidence, Voyager 2 would still be traveling, or more likely would have never launched. But even with all these gravitational assists, the journey remained epic. Think about it. When Voyager 2 passed Jupiter, Jimmy Carter was president of the United States. When it reached Saturn, it was already the Reagan era. By Uranus, the Challenger disaster was fresh in memory. And when it finally arrived at Neptune, the Berlin Wall was about to fall. An entire historical epoch had passed while this little probe traveled through cosmic darkness. On August 25, 1989, finally Voyager 2 reached Neptune. It passed just 3,000 miles or 4,950 kilometers from the planet's North Pole. In space terms, that's like brushing a hair. Considering it had traveled over 4.3 billion miles or 7 billion kilometers, hitting a target with such precision is like shooting an arrow from New York and hitting a coin in Los Angeles. In those few frantic hours of flyby, the probe had to do years' worth of work. Photograph the planet, its moons, its rings. Yes, Neptune has rings too, though they're pretty pathetic. Measure the magnetic field, analyze the atmosphere, all while screaming past at insane speed and with radio signals taking 4 hours to reach Earth. The discoveries were sensational. Neptune revealed itself as a dynamic world with the fastest winds in the solar system, up to 1,300 miles per hour, or 2,100 kilometers per hour, almost twice the speed of sound on Earth. There was a great dark spot, similar to Jupiter's but more transient. Triton, the main moon, turned out to be geologically active, with nitrogen geysers shooting dark material up to 5 miles or 8 kilometers high. It was like discovering that Earth's most remote desert hides active volcanoes. And then nothing. Voyager 2 continued its race towards infinity, and no other probe has visited Neptune since. More than 30 years have passed, and everything we know about that world still comes from those few hours of observation in 1989. It's like we explored Australia by flying over it once, at night, with a flashlight. Why haven't we gone back? The reasons are many, and they all boil down to one word: difficulty. Neptune is damn far, damn cold, and damn complicated to reach. At that distance from the Sun, light is 900 times fainter than on Earth. Solar panels? Forget about them. A panel that generates a kilowatt on Earth would barely produce a watt there. You need nuclear generators, and the plutonium-238 that powers them is rarer than reunion tour tickets for the Beatles. The United States only recently resumed production after a decades-long pause, and they produce just 3.3 pounds or 1.5 kilograms per year. A mission to Neptune would need at least 22 to 33 pounds or 10 to 15 kilograms. Then there's the cold. On Triton, Neptune's main moon, temperatures drop to minus 391 degrees Fahrenheit or minus 235 degrees Celsius. It's one of the coldest places in the solar system, a place where nitrogen we breathe is solid as rock, and electronics malfunction just thinking about it. At those temperatures, metal becomes brittle as glass, lubricants solidify, batteries stop working. Designing a probe that survives in those conditions is an engineering nightmare. You need heaters, special insulation, redundant components. Everything weighs, everything costs, everything can break. And communication times: 4 hours to send a command, 4 hours to receive a response. 8 hours of waiting for a "Hi, how are you? I'm fine. How about you?" When you're controlling a probe near Neptune, it's like playing chess by mail with someone living in another era. You have to program everything in advance, hope nothing goes wrong, and cross your fingers. If something malfunctions, by the time you notice, it's already too late to fix it. The probe has to be smart enough to handle things on its own. But above all, there's the money question. A mission to Neptune costs billions, not just to build the probe, but to keep it operational for all those years of travel. You need giant antennas on Earth to communicate, teams of engineers and scientists working for more than a decade, computers and software continuously updated. It's an investment that makes even the richest space agencies' hands shake. For the price of one Neptune mission, you could send a dozen rovers to Mars. There's also the launch window problem. You can't just leave whenever you want. To take advantage of Jupiter's gravitational assist, practically indispensable if you don't want to wait 30 years, you have to launch when Jupiter and Neptune are in the right position. This happens every 12 to 13 years. The last good opportunity was in 2018-2019. The next will be in 2031-2032. If you miss it, good luck and goodbye. See you in another decade plus. Yet despite everything, the idea of returning to Neptune isn't dead. In fact, in recent years, increasingly ambitious proposals have emerged. There's Neptune Odyssey, an orbiter that could launch in the early 2030s and arrive in the late 2040s. Yes, you heard that right, a journey of almost 20 years. But at least it would stay in orbit for years, not like the Voyager, which just rushed past. The project envisions 46 Triton flybys, complete planetary mapping, atmospheric and magnetic field studies. Estimated cost $3.4 billion, not exactly pocket change. There's an even crazier idea called Triton Hopper. Imagine a robot that lands on Triton and then hops from place to place using the moon's frozen nitrogen as fuel. It collects the ice, heats it up, expels it as propellant, and hop, jumps a few miles. Brilliant if we could make it work at minus 391 degrees Fahrenheit or minus 235 degrees Celsius. Earth tests are promising, but it's one thing to do them in a lab, another to do them on a moon 2.8 billion miles or 4.5 billion kilometers from home. The Chinese have announced they want to send something to Neptune around 2030, and knowing them, they'll probably pull it off. They're talking about nuclear propulsion, which could shorten travel times. But even so, we're talking about a decade plus. Their Interstellar Express mission could use a nuclear reactor to power super-efficient ion engines. Science fiction? Maybe, but the Chinese have a habit of turning science fiction into reality. The future could be brighter. Nuclear thermal propulsion, electric propulsion, maybe someday fusion. All technologies that could transform Neptune from an impossible destination to merely a difficult one. Nuclear thermal propulsion could cut travel times in half, bringing them down to 6 to 8 years. Not bad, but it requires nuclear reactors in space, and not everyone's thrilled about that idea. There are even visionaries talking about solar sails as big as cities, pushed by sunlight to unthinkable speeds. Or plasma propulsors that accelerate for years, slowly but relentlessly to speeds that chemical rockets can only dream of. But for now, they're just dreams, drawings on university lab whiteboards. The truth is that Neptune will probably remain the solar system's last frontier for a long time yet. It's too far, too cold, too difficult. But that's exactly what makes it fascinating. It's a world where winds blow at supersonic speeds, where it rains diamonds. Seriously, atmospheric pressure can crystallize carbon, where a moon as big as ours orbits backward compared to all other satellites. A world that hides mysteries that could revolutionize our understanding of how planets form and evolve. Consider that Neptune emits more energy than it receives from the Sun. How? We don't know. Its magnetic field is tilted 47 degrees from the rotation axis and offsets 0.55 planetary radii from the center. Why? Mystery. Triton orbits retrograde, a sign it was probably captured from the Kuiper Belt. But how? When? All questions without answers. 12 years to get there. Is that a long time? Depends on how you look at it. For a space mission, it's an eternity. For the universe, it's a blink of an eye. For humanity, it's a challenge we'll take on again sooner or later. Because if there's one thing we've learned in these decades of space exploration, it's that the impossible is just a matter of time and determination. Meanwhile, Neptune continues its slow dance around the Sun, completing an orbit every 165 Earth years. The last time it was in its current position, cars and planes didn't exist, let alone space rockets. Darwin was about to publish On the Origin of Species, and America was about to begin its Civil War. The next time it comes around in 2176, who knows, maybe we'll have already been there in person. Maybe we'll have colonies on Mars and space hotels in Earth orbit. Or maybe we'll still be here wondering how the hell to get there in less than a decade. But that's another story, and it will take far more than 12 years to tell. For now, let's be content to look at that blue dot in Voyager 2's photograph and dream of the day we'll return to visit the last of the giants. It won't be easy, it won't be fast, but hey, the best things take time. And Neptune, out there in the cold and darkness, has all the time in the universe to wait for us. After all, what's a century or two for a planet that existed for 4.5 billion years?